Hello there, and welcome to Sleepy Traveler. Thank you for choosing this quiet moment to rest your mind with me. Wherever you are right now, let the thought of the outside world gently recede, much like a quiet tide pulling back from the shore. We are settled here, safe and unhurried. Tonight, we will turn our focus not to the vast, cold emptiness above, but to the deep, consistent warmth of the world beneath our feet. Our planet holds a secret heart, a solid, glowing core 4,000 miles down, a place we can only reach with our imagination. It is a slow, quiet furnace of iron and nickel, a source of stable energy that has protected our lives for billions of years. We will journey down through the silent layers, the crust, the mantle, the outer core, following the whispers of seismic waves until we feel the ancient, steady rhythm of the center. We move with great care, letting the physics feel like a cozy, reliable truth. If this gentle journey inward brings you comfort or helps your thoughts grow soft, a quiet like and a soft subscribe are the gentle way we invite others to share in this unique calm. When you're ready, let's begin our quiet descent to the Earth's warm, secret core. Beneath your feet there is a hidden world, stranger than the night sky above. It is a realm of weight and heat and metal, pressed and stirred in the dark. To reach the deep heart of our planet, you would have to travel nearly 4,000 miles inward, passing through shifting plates and rock that can move like a very slow liquid. Far below, the Earth keeps an iron heart, almost as hot as the glowing face of the Sunday. No human will ever stand there, yet this unseen interior quietly shapes almost everything we know on the surface. It guides the drifting of continents, feeds volcanoes, and helps maintain the magnetic shield that wraps our world and turns away dangerous winds from space. The long descent begins at the ground you know so well and then slips through layers that grow stranger with every mile. What feels solid under your feet is really only a thin shell. The crust, the material we live on, is like the skin of a fruit or the shell of an egg, compared with the whole globe. Beneath the oceans, this shell is only a few miles thick, mostly dark, volcanic rock called basalt. Under the continents, it swells to several tens of miles, built of lighter rocks such as granite. But measured against a planet whose radius is thousands of miles, all of that is just a delicate coating. Even so, we have barely touched it. The deepest artificial hole ever drilled, the Kola super deep borehole in Russia, reached only a handful of miles into the crust, just a tiny fraction of the way toward the center. Yet even there, the rocks were far hotter and more squeezed than scientists had expected, hinting at how quickly conditions change as you go down. Below this fragile shell lies the mantle, which makes up most of Earth's volume. It is not a vast ocean of lava, the way many imagine. It is solid rock, but rock under such pressure and heat that over immense stretches of time, it can slowly flow. To us, it would feel hard and stubborn in the hand. Over millions of years, it behaves more like thick honey, creeping and folding. This is the region that supplies the energy for earthquakes and volcanoes and the slow drift of continents. When a slab of ocean floor slides beneath another at a subduction zone, it does not vanish. It sinks into the mantle, carrying bits of our surface world with it. Water, carbon, and subtle chemical traces of life. In that way, the deep Earth is constantly swallowing and recycling tiny pieces of oceans and seafloors, folding them into its own slow motion. We know there is a boundary between crust and mantle, not by sight, but by listening to the planet's shivers. When an earthquake ripples through the Earth, it sends out seismic waves that spread in all directions. As these waves pass into different kinds of rock, they change speed. At a certain depth, they suddenly quicken, as though they have crossed a hidden doorway into a new material. That jump in speed marks the end of the crust and the beginning of something deeper. The top of the mantle is far from quiet. It reaches up toward the crust, breaks it, thins it, and sometimes builds it anew. Where hot material rises, it can stretch the surface apart, opening rifts like the East African Rift Valley, or lifting long mountain-like ridges on the ocean floor, where new seafloor is born. Where cold, old ocean crust sinks back down, it drags the mantle with it, stirring these deep rocks like a slow spoon in a thick batter. This endless cycle of rising and sinking is one reason Earth is still geologically alive, unlike Mars or our moon, whose interiors have mostly gone still. Our planet's surface is always being created, destroyed, and remade by the hidden movements beneath. Even within the upper mantle, there are quiet surprises. Under enormous pressures, carbon atoms can crystallize into diamonds. These gemstones, hard and bright, sometimes carry tiny passengers from far below, microscopic grains of deep minerals trapped inside them when they formed. By studying those inclusions, scientists have been able to see which kinds of rocks exist hundreds of miles down, where we will never drill. Some diamonds even hold minuscule droplets of water, sealed like ancient letters. Those droplets hint that the deep Earth may contain far more water than anyone expected, perhaps amounts that rival or even exceed all the water in our surface oceans. If so, then there is a hidden, dark reservoir, a deep memory of water woven through the mantle. For decades, geologists have dreamed of reaching the mantle directly with a drill. In the 1960s, an ambitious effort called Project Mahole tried to pierce the thin ocean crust, since it is the shortest route to the mantle. Costs and difficulties eventually ended the attempt, but the dream lingered. More recently, Japan's research ship Chikyu has bored into the sea floor, trying to approach the boundary between crust and mantle. The problem is not only depth, but the harshness of the conditions. Rock so hot it can soften and destroy drill bits, and pressures that squeeze every piece of equipment like a clenched fist. As you pass from crust into mantle, the very recipe of the Earth changes. The crust is rich in lighter elements, silicon, aluminum, oxygen, and others that make the familiar rocks of mountains and continents. The mantle is heavier and darker, dominated by minerals such as olivine and peridotite, often greenish stones that rarely reach the surface unless a volcanic eruption drags them up. Under the enormous pressures inside the planet, even these tough minerals can transform into new structures with different names and shapes. Deeper down, olivine changes into forms called wadsleyite and ringwoodite, minerals that cannot survive at the surface but whisper to scientists about the pressures and temperatures in the hidden depths where they exist. Clues to these transformations often come from those same diamonds, which capture tiny grains of these deep minerals and carry them upward when they are brought to the surface. Our understanding of the crust-mantle boundary took a great leap forward in 1909, thanks to a Croatian seismologist named Andrija Mohorovičić. He studied earthquake waves recorded at stations across his region and noticed something peculiar. Some waves arrived sooner than they should have, as if they had found a faster road inside the Earth. The simplest explanation was that they had dipped below the crust into a denser layer where they could travel more quickly. From this insight, came the idea of a distinct boundary, a sharp change from the lighter rocks of the crust to the denser rocks of the mantle. That boundary now bears his name and is often simply called the Moho. We still have never reached it, but we can trace it with waves. The Moho is not at the same depth everywhere. Under ocean basins, where the crust is thin, it lies only a few miles beneath the seafloor. Under continents, especially old, thick ones, it can sink to several tens of miles. In theory, drilling through the ocean crust should let us touch it sooner. In reality, even that shorter path is blocked by extreme heat, high pressure, and the stubborn strength of deep rock. When the Earth shakes, it sends out two main kinds of seismic waves. One compresses material back and forth like sound. The other shears it side to side. Both types speed up when they pass from softer, lighter rocks into harder, denser ones. Mohorovičić realized that the sudden speeding up of certain waves meant they had entered a region where minerals are packed more tightly together. That was the first strong proof that our planet is layered, not uniform all the way through. Above the Moho, the crust is mostly granite on land and basalt under the seas. Below it, the mantle's denser minerals dominate. This change in rock type explains the jump in wave speed. In a way, the Moho is like the line between Earth's outer skin and its deeper muscles, between the familiar world of mountains and oceans and the hidden one that moves them. For a long time, many imagined the Moho as a perfectly sharp line everywhere, but as seismic methods have grown more precise, a more complicated picture has emerged. In some regions, the transition seems fuzzy rather than crisp, spread over a thickness of several miles. That suggests that melting, mixing, and even traces of trapped water can blur the line between crust and mantle. Reality is messier than the neat diagrams in textbooks. There is also evidence that the Moho plays a role in the way water moves into and through the deep earth. Rocks from volcanoes that tap areas near this boundary sometimes contain more water than expected, stored in their minerals. This has led some researchers to imagine the Moho as a kind of filter or gate, where slabs of ocean crust sinking into the mantle begin to release the water they carried down. That water lowers the temperature at which rocks melt and can help feed volcanic eruptions above. In this sense, the Moho is not just a quiet dividing line drawn on a page. It may participate in earthquakes, volcanoes, and the long recycling of Earth's surface. In regions with active faults, like parts of California or Japan, seismic studies suggest that the Moho can be bent, warped, or cracked. Forces that crumple the crust can tug on the mantle as well, reshaping the boundary over millions of years and opening pathways for magma to rise toward the surface. By mapping the depth of the Moho across continents, geophysicists have also learned about the hidden roots of land masses. Very old continental regions tend to have a deeper, more stable Moho than younger, more recently assembled terrains. In this way, the Moho acts like a kind of fossil record, written in rock thickness instead of bone, preserving the history of how continents grew, collided, and changed over billions of years. Deeper into the mantle, the image of stillness gives way to a slower, stranger kind of motion. We usually think of rivers as flowing water, but inside Earth, there are rivers of solid rock. The mantle extends for roughly 1,800 miles below the crust. If you could somehow hold a piece of it, it would feel hard and heavy. Yet over spans of time far longer than a human life, that same rock can creep and stream. This slow movement is called mantle convection. Heat from the deep earth is always trying to escape. When rock near the bottom of the mantle is warmed, it becomes a little less dense and starts to rise. Near the top, where it cools, it grows heavier and sinks again. The cycle is like the swirling of water in a gently boiling pot, except that here it takes place in solid rock across an entire planet, and the boiling unfolds in inches per year. Those inches are enough. Over millions of years, the slow motion of mantle rock reshapes the face of the world. Where hot mantle rises, it can lift and split continents, opening new ocean basins. Along mid-ocean ridges such as the one that winds down the middle of the Atlantic, mantle rock melts and wells up, forming new crust as seafloor spreads apart on either side. Where cooler, denser portions sink, they drag oceanic crust down into subduction zones, like those around the Pacific Ring of Fire. Without these slow rivers of stone, there would be no plate tectonics, no mountains built by collision, no long chains of volcanoes. The Earth's surface would grow old and quiet, more like the moon's, its story frozen in place. For a long time, scientists pictured mantle convection as a set of simple rolls, one loop rising, one loop sinking. But as seismic imaging has improved, the picture has become tangled and richly detailed. Some rising plumes are slim and focused, like the one thought to feed the volcanoes of Hawaii. Others are wide, spreading currents that push gently on the underside of whole continents. Sinking slabs of ocean crust sometimes plunge all the way to the bottom of the mantle. Other times, they stall halfway down, piling up in deep traffic jams. Still deeper, between roughly 400 and about 650 miles down, lies what is called a transition zone. In this region, the crushing pressures force mantle minerals into new crystal forms. These changes can act like a series of speed bumps for the mantle's slow rivers, deflecting or slowing them. Some rising plumes manage to punch through and carry heat to the surface, feeding volcanic hotspots. Others flatten and spread out, unable to cross the barrier. Likewise, some sinking slabs pause and accumulate there before sinking farther. This hidden choke point may help explain why some regions of Earth are dotted with volcanoes, while others stay quiet. The mantle's slow rivers carry more than heat. They also carry water and carbon, the quiet ingredients of oceans and life. When oceanic plates descend into the mantle, they drag along minerals that hold water within their crystal structures, as well as carbonates and other carbon-bearing compounds. These can travel hundreds of miles down before conditions free them again. Some of the water released at depth helps mantle rocks melt at lower temperatures, fueling magmas that rise toward the surface and feed volcanoes. Some of the carbon eventually returns to the air through volcanic gases, closing a vast, slow loop known as the deep carbon cycle. Over millions of years, this cycle helps regulate the Earth's temperature, balancing the storage and release of carbon between the surface and the interior. In this way, the mantle quietly stores, moves, and returns the basic building blocks of oceans and air. There is one more thread tying these deep motions to the life above. Earth's magnetic field is generated in the outer core, a layer of liquid metal beneath the mantle. But the way heat escapes through the mantle helps control how vigorously that liquid metal stirs through the slow rivers of the mantle. The amount of heat leaving the core is regulated. If mantle convection were to slow greatly, it could change the core's behavior and weaken the magnetic field that shields us from harmful solar radiation. This means that the mantle is not only a natural engine, but also a system that keeps life on Earth going. Deep inside that slow, living mantle, there is a quieter mystery resting in the middle depths. A few hundred miles beneath us lies a band of rock that behaves differently from the layers above and below. We cannot see it, but earthquakes and tiny samples pressed in laboratories reveal its outline. Geophysicists call it the mantle transition zone, and many now think it may be one of the largest hidden reservoirs of water on Earth. This zone exists because minerals change their shape under immense pressure. Near the surface, much of the mantle is made of olivine, a green crystal that sometimes appears in volcanic rocks. Deeper down, as the weight of overlying rock increases, olivine rearranges itself into denser forms called wadsleyite and ringwoodite. These versions cannot survive at the surface. If they rise, they relax back into ordinary olivine, but in the depths where they belong, they make up a vast belt circling the planet. What makes wadsleyite and ringwoodite remarkable is their ability to hide water inside their crystals, not in pools or droplets, but as tiny groups of atoms tucked into their structure. In the laboratory, under pressures like those hundreds of miles down, these minerals can hold a few percent of their weight as water spread through the volume of the transition zone that becomes enormous. Some estimates suggest that, taken together, the water locked there could rival or even exceed all the water in our oceans. In 2014, a small diamond from Brazil offered the first direct hint that this hidden ocean is real. Trapped inside was a microscopic grain of ringwoodite. When scientists studied it, they found it contained water, clear proof that rocks at those depths are not dry. It confirmed what many had suspected from the way seismic waves slow and speed inside the planet. There are wet places deep beneath our feet. If the transition zone truly acts as a giant reservoir, it quietly influences the surface world. Water lowers the temperature at which rock begins to melt, making it easier to form magma. A water-rich transition zone could help decide where magmas are born and how they rise, shaping which regions become volcanically active. Some unusually wet magmas that feed hotspots like Hawaii or Iceland may be receiving small, steady leaks of deep water from this buried storehouse. Water also softens rock, making it more able to deform. If some parts of the transition zone are wetter than others, rocks there will flow more easily. That could speed up mantle motion beneath certain regions and slow it beneath others, stirring the planet unevenly and helping to explain why some areas flare with volcanoes and earthquakes, while others stay calm for ages. This middle layer also affects the fate of sinking plates. When slabs of ocean crust dive into the mantle at subduction zones, many reach the depths of the transition zone. Some slices of slab plunge through and continue into the lower mantle. Others flatten and spread, stacking like crumpled sheets. As olivine changes to denser minerals, parts of the slab are encouraged to sink. Deeper down, new changes can briefly resist that motion, stalling slabs in this band for millions of years before they break through. Seismic images reveal regions within the transition zone where earthquake waves slow, hinting at patches of partial melt. Those may be pools of magma fed by water released from the sinking slabs themselves. When minerals that carried water down begin to heat and transform, they can free that water, which in turn makes nearby rock melt more easily. These hidden melt pockets may help feed powerful eruptions far above, linking quiet reactions in the dark to fiery events at the surface. Because we cannot travel to these depths, scientists recreate them in miniature. With diamond anvils and powerful lasers, they squeeze and heat tiny grains of rock to the pressures and temperatures of the deep earth. By watching how minerals such as ringwoodite behave and how much water they can absorb, they build a picture of a transition zone that is dynamic, water-bearing, and deeply involved in the way Earth's interior engine runs. Below that water-rich band, the story of slabs continues. Earth's shell is constantly broken and drawn downward, and the sinking pieces do not simply vanish. Instead, they gather in what some call the slab graveyard, an underworld where old ocean floors go to rest. By listening carefully to earthquake waves, scientists have found regions in the mantle that are colder and denser than their surroundings. Their shapes and paths match the routes of plunging plates, as if we are seeing the shadows of entire tectonic slabs preserved far below the surface. Most of these slabs begin at deep-sea trenches, where one plate dives beneath another. They carry sediments, water, and the chemical traces of long-vanished oceans and life. Being colder and heavier than the mantle, they sink like stones in thick syrup, yet their journeys are varied. Some dive almost straight into the lower mantle. Others stall near the transition zone, curl, fold, or break apart under immense pressure. The slab graveyard is not the same everywhere. In some parts of the world, slabs appear to gather near the base of the mantle, just above the liquid outer core. There, they may linger for hundreds of millions of years as cold ridges and piles in a sea of hotter rock. Elsewhere, slabs look shredded and mixed into the mantle flow, or partly melted into strange patches where seismic waves slow to a crawl. All of this paints the mantle not as a neat conveyor belt, but as a restless engine with eddies, bottlenecks, and deep storage rooms. Evidence is growing that some slabs really do reach the very bottom of the mantle and spread along the boundary where rock meets the outer core. Seismic studies show thick curtains of denser material extending downward from subduction zones to those depths. If that is so, these slabs may store a long record of plate tectonics, preserving arrangements of continents and oceans that the surface has long since erased. Their presence may even steer where hot plumes rise from the boundary, channeling heat toward particular regions. Some researchers think that enormous volcanic events in Earth's past, including those that built vast lava plateaus, may have been triggered where old slabs changed the pattern of deep flow and helped focus rising plumes. As they descend, slabs also carry water and carbon. Hydrated minerals and carbon-rich sediments ride downward with the sinking crust. Some of that material is released at shallower depths, feeding chains of volcanoes near subduction zones. Much of it continues into the deep interior. In this way, the slab graveyard may act as a giant vault, hiding away deep stores of water and carbon far beneath the crust. Over millions of years, some of this buried material leaks back upward, completing a slow cycle that links the deep earth with the air and oceans above. This continual recycling is one reason Earth is so different from many other rocky worlds. Mars and the Moon show no sign of active plate tectonics. Without plates that sink and are reborn, their interiors have cooled and stiffened, and their surfaces have been frozen in old stories for a very long time. Earth, by contrast, has been reusing its own skin for billions of years. The slab graveyard beneath us is quiet proof that plates have been diving, piling up, and melting back into the mantle since the planet was young. Some scientists think the slab graveyard may hold even older secrets. Ancient slabs could remain parked near the core mantle boundary for more than 1 billion years. If so, they might preserve traces of Earth's earliest crust, long since erased from the surface, by erosion and collision. There are hints in seismic data that some buried slabs may be relics of supercontinents that existed hundreds of millions of years ago. In that sense, the slab graveyard is not only a place of rest, but also a time capsule, keeping the memory of past worlds sealed in stone. Just above the outer core lies another strange realm, one of the most puzzling layers inside the planet. It occupies only a few hundred miles, at the very base of the mantle, pressed hard against the liquid metal below. Seismologists often call it the D double prime layer, and it may hold clues to some of Earth's deepest riddles. This layer first revealed itself through odd behaviors of earthquake waves near the core mantle boundary. At those depths, some waves race as if through unusually stiff rock, while others slow as if passing through partially molten or chemically unusual material. Unlike the layers above, which tend to be more uniform over large regions, this base layer is patchy and irregular, a quilt of different zones stitched together by the planet's long history. One leading idea is that this is where many subducted slabs finally come to rest. After sinking thousands of miles, cold, thick pieces of old ocean crust may spread out along the base of the mantle, forming rugged highlands where rock presses against liquid metal. There, seismic waves would move faster as they cross dense, solid piles of ancient seafloor. Nearby, some of the slab material may melt or react with hotter mantle, creating pockets of partly molten rock where waves slow down. In this way, the base of the mantle may have deep mountains and valleys, all carved from the remains of plates that once lay at the bottom of ancient seas. This deepest mantle layer seems tied closely to mantle plumes, hot upwellings that feed volcanic hotspots such as Hawaii and Iceland may begin as concentrated blobs of overheated rock at or just above this boundary. In that picture, the D double prime layer is a plume nursery where heat from the outer core gathers until it breaks upward in focused columns. Differences in its structure from place to place could help explain why some plumes are enormous and persistent, while others are smaller or absent entirely. High-pressure experiments add another twist. Under the extreme conditions near the core, familiar mantle minerals may transform into a new phase, known as post-perovskite. This mineral appears to conduct heat differently and may account for some of the odd seismic signatures seen in D double prime. If it is common there, it could strongly influence how heat escapes from the core, how plumes are launched, and how stable the magnetic field remains over time. Because this layer sits directly on top of the core, it helps regulate how that deeper heart stays warm. Heat must flow through D double prime on its way out. If some regions conduct heat more efficiently than others, the liquid outer core beneath will convect more vigorously in some places and more slowly in others. That uneven churning can imprint itself on the magnetic field above, perhaps contributing to regions where the field at the surface is weaker than average. Seismic scans suggest that the base of the mantle is not smooth. Instead, it has deep hills and hollows, some rising or falling for several miles. At the surface, mountains are built where plates collide and crumple the crust. In the deep earth, the mountains of D double prime may be formed where old slabs ram into the core mantle boundary and pile up. It is a hidden landscape of rock pressed against metal, far below any ocean or continent. Beneath that rough, rocky floor lies a very different realm. Far under our feet, the solid mantle gives way to the outer core, a vast ocean of liquid metal. This layer is mostly molten iron, mixed with nickel and lighter elements, and it is far thicker than any surface sea. Unlike the solid mantle above and the solid inner core below, this region flows and churns, restless and hot. We learn that the outer core is liquid by listening to earthquakes. Some seismic waves cannot travel through liquid at all, while others slow as they cross from solid into fluid. Careful studies in the early 20th century showed that, at certain depths, these waves vanish or bend in exactly the way they would if they had encountered a shell of liquid metal wrapped around a solid inner heart. That realization reshaped our picture of Earth. Not a single solid ball, but a solid center surrounded by a moving metallic sea. The conditions in the outer core are extreme. Temperatures range from roughly 4,000 to more than 6,000 degrees Celsius, comparable to the surface of the sun, while pressures are millions of times higher than at sea level. Under such extremes, iron and nickel, which would be hard and rigid on the surface, remain molten and mobile. The outer core is the largest fluid body on Earth, dwarfing all of our oceans, even though no human eye will ever see it. This ocean of metal powers the planet's magnetic field. As the liquid iron and nickel flow, they carry electric charges with them. Combined with Earth's rotation, these moving charges create a dynamo, turning the core into a planetary-scale generator. The magnetic field that emerges extends far into space, forming the magnetosphere that deflects the solar wind and shields our atmosphere from being slowly stripped away. Without this invisible bubble, Earth's air and water might have been lost long ago. The motion of the outer core is organized into great convection currents. Heat leaks outward from the inner core and from radioactive elements, causing hotter, lighter fluid to rise, while cooler, denser fluid sinks. Because the planet spins, these flows twist and spiral into complex patterns. Some areas churn more strongly than others, creating regions where the magnetic field is especially strong, and others where it is weaker and more tangled. The way heat escapes from the outer core also touches the mantle, where more heat flows through the core mantle boundary. Mantle rock above may become buoyant and rise, feeding plumes that can lead to volcanic hotspots at the surface. In this sense, the hidden motions of the outer core quietly influence where volcanoes form and where continents slowly shift, even though they lie thousands of miles below. The magnetic field that protects us is not fixed. Measurements show that the magnetic poles wander and that the field sometimes weakens, strengthens, and even flips, with north and south trading places over long spans of time. These changes are linked to the ever-evolving flow patterns in the outer core. As currents rearrange themselves, the shape and strength of the magnetic field above respond. There are hints that even this molten layer is not perfectly uniform. Some studies suggest that the very top of the outer core may differ slightly from the deeper fluid below, perhaps because of chemical exchanges with the mantle, or because certain elements are slowly freezing onto the growing inner core. If so, the outer core is not just a simple, featureless ocean of iron. It is a layered, chemically active region whose currents and compositions are always in slow motion, quietly reshaping the magnetic shield and, with it, the conditions that make our surface world possible. Deep inside that vast ocean of metal, the story turns to the engine that keeps it moving. If the outer core is a restless sea, then the dynamo effect is the hidden machine it drives, turning quiet motion into an invisible shield that stretches far into space. That shield is Earth's magnetic field. It bends the stream of charged particles from the sun, keeps most of the harsh cosmic radiation from reaching the ground, and helps our atmosphere stay wrapped around the planet instead of being slowly stripped away. Without it, the oceans might not have lasted long enough for life, and the surface we know would feel very different. The engine itself is built from heat, spin, and flowing metal. Heat rises from the solid inner core and from the slow decay of radioactive elements, as well as leftover warmth from Earth's beginning. That heat makes parts of the liquid iron slightly lighter, so they rise, while cooler, heavier fluid sinks. This gentle but persistent overturning is convection, the same basic process that makes water roll in a simmering pot. But here the pot is the size of a world, and everything is made of glowing metal. Because Earth rotates, those rising and sinking currents cannot simply flow straight up and down. They twist into great spirals under the influence of the Coriolis effect, the same subtle force that helps organize hurricanes in the atmosphere. As molten iron and nickel move through these spirals, they carry electric charge with them. Moving charges create magnetic fields. When those flows are strong and organized enough, the small fields they create feed back into the motion, guiding the currents and strengthening the field in return. The result is a self-sustaining loop. Motion creates magnetism. Magnetism influences motion, and the system keeps itself going. This is the heart of the dynamo effect, a churning, electrically active engine that has kept Earth's magnetic shield alive for a very long time. But it is not a perfectly steady machine. The field it generates wobbles and drifts. Regions of unusual weakness appear, such as the South Atlantic anomaly, where the field at the surface is softer than average, likely because the flows of metal beneath are temporarily out of their usual pattern. Even the magnetic poles do not stay put. Over longer spans of time, the dynamo becomes even more dramatic. The magnetic field has flipped many times in Earth's history, with north and south trading places. Rocks on the seafloor record these reversals in alternating bands. During a reversal, the field weakens, becomes tangled, and eventually reforms with opposite polarity. The last major flip happened roughly 780,000 years ago. These events do not seem to be catastrophic for life, but they reveal how restless the deep engine really is. The dynamo is closely tied to the growth of the inner core. As Earth slowly cools, iron in the outer core crystallizes and freezes onto the top of the solid inner core. Each tiny crystal that forms releases heat and lighter elements back into the surrounding liquid. That extra heat and buoyancy feed convection, stirring the outer core and keeping the dynamo energized. In a quiet way, the slow growth of the inner core keeps the generator running. Without that continuing supply of energy, the flows could weaken and the magnetic field might fade, as seems to have happened on Mars long ago. Experiments give us small echoes of this deep process. In spinning metal-filled devices, moving liquid can generate magnetic fields on its own, showing that the same basic physics can arise even on a human scale, a miniature reflection of Earth's hidden engine. At the very center of all this motion lies the inner core itself, a solid sphere of iron and nickel, almost 1,500 miles across, sitting nearly 4,000 miles beneath our feet. Though we will never see it directly, it is one of the most important parts of the planet. It is roughly 70% the size of the moon, a dense metal heart beating in darkness, shaping the world above in ways we are only beginning to grasp. The inner core exists under conditions that push imagination to its limits. Temperatures there are estimated to reach more than 5,000 degrees Celsius, close to the heat of the sun's visible surface. Pressures are millions of times greater than what we feel at sea level. Under such crushing conditions, iron and nickel, which are molten in the outer core, are forced into a solid crystalline state at the very center. The paradox is striking. It is hot enough to melt metal, yet the pressure is so extreme that metal is squeezed into solidity. The result is a compact lattice of atoms forming Earth's central sphere. We know this inner core is real because of the way seismic waves pass through the Earth. Powerful earthquakes send vibrations through the globe. Some of these waves can travel through both solids and liquids, while others can only move through solids. By mapping how fast these waves arrive at stations around the world and where they speed up or slow down, scientists can infer the materials they have crossed. In 1936, a Danish seismologist named Inge Lehmann noticed patterns that could only be explained by a solid inner ball inside the liquid core. Her insight revealed the iron heart at Earth's center. Far from being a static lump, the inner core is slowly growing. As the planet cools, the outer core loses heat, and iron begins to crystallize at the inner core boundary. Each newly frozen layer joins the solid sphere, causing it to expand by about 1 millimeter each year. That sounds tiny, but over long spans of time, it adds up to a structure that did not always exist in its current form. Some studies suggest the inner core may have solidified relatively late in Earth's history, perhaps within the last 1 billion years. This growth is not just a curiosity. It is tied intimately to life at the surface. As iron solidifies at the boundary between inner and outer core, it releases heat and lighter elements, which help drive convection and sustain the dynamo. In other words, the freezing of the inner core feeds the motion of the outer core, which maintains the magnetic field that protects our atmosphere and oceans. If this process were to slow, the core could gradually quiet down, and Earth's protective shield might fade. The inner core itself is not uniform. Seismic waves passing through it travel faster in some directions than others, a property known as anisotropy. This suggests that the iron crystals inside may be aligned in preferred orientations, possibly influenced by Earth's rotation or by the way the core has cooled over time. There are hints that one hemisphere of the inner core may be crystallizing faster than the other, creating a subtle lopsidedness deep at the center of the planet. The reasons for this asymmetry remain uncertain, but they could influence how the magnetic field behaves over very long timescales. The age of the inner core is still debated. Some evidence points toward a relatively young age of a few 100 million to around 1 billion years, while other studies allow for a much older core. Knowing that age would change our picture of how long the strong magnetic field has wrapped the planet and how Earth's deep interior has evolved. Another mystery involves how the inner core turns. It is not necessarily locked perfectly to the rest of Earth. Some seismic studies suggest that the inner core may rotate at a slightly different speed than the mantle and crust above, sometimes a little faster, sometimes a little slower. This is called superrotation. Early estimates said the inner core might gain an extra turn every few centuries. That may not sound like much, but for something so massive, any difference is remarkable. It implies that the inner core is interacting dynamically with the liquid outer core and the overlying mantle. The likely cause of this superrotation is the tug of electromagnetic forces. As the outer core's flowing metal generates the magnetic field, it can exert a twisting torque on the solid inner core, nudging it to spin ahead. At the same time, the mantle's gravity pulls on slight irregularities in the core, trying to keep it aligned. The balance between these pushes and pulls may cause the inner core's rotation rate to drift over decades and centuries. Some work even hints at cycles, with the inner core speeding up and slowing down on a time scale of several decades, and subtly linked to tiny changes in the length of our day. These ideas are still being tested. We cannot place instruments directly in the core, so scientists must rely on seismic waves from earthquakes and other strong vibrations to probe the deep interior. The signals are faint, and small changes can be interpreted in different ways. Some researchers are convinced that superrotation is real and measurable. Others argue that variations in the structure of the inner core itself might explain the observations without requiring changes in rotation. For now, the very heart of Earth keeps some of its rhythm to itself. At the boundary between the inner and outer core, another important frontier appears. This inner core boundary is the thin shell where solid iron meets the surrounding ocean of liquid metal. It lies more than 3,000 miles below our feet, yet it marks one of the sharpest transitions anywhere inside the planet. On one side, atoms are locked into a rigid lattice. On the other, they flow past one another in slow, rolling currents. Seismic waves feel this change immediately. They speed up when they enter the solid inner core and slow dramatically in the liquid outer core. That contrast is so strong that scientists can locate the boundary to within only a few miles. Conditions at this frontier are extreme. Temperatures exceed 5,000 degrees Celsius, but just above the boundary, the pressure is slightly lower, allowing iron to remain molten. Just below, the higher pressure forces iron and nickel into solid form. In that narrow zone, liquid becomes solid, and the inner core grows. This surface is not just a line on a diagram. It is an active workshop where new inner core is forged and energy is released to fuel the dynamo. The inner core boundary is likely not smooth or perfectly even. Seismic studies suggest that some regions are rougher or more irregular than others, with waves arriving a little faster or slower than expected. This could mean that iron crystallizes at different rates around the core, making one side slightly thicker than the other. There are hints that the inner core may be growing faster under one hemisphere, reinforcing the idea of a lopsided heart. Chemical changes also occur here. As iron solidifies, it tends to exclude lighter elements such as oxygen, sulfur, or carbon, pushing them back into the outer core. Those lighter components may accumulate in layers just above the boundary, affecting how the liquid metal moves. Subtle variations in composition can alter convection patterns and may help explain some of the oddities we see in Earth's magnetic field. In this way, the inner core boundary acts as both a physical and chemical dividing line, helping to shape the dynamics of the entire core. There are even signs that the very center of the inner core may differ from its outer parts. Some seismic paths hint at a tiny inner core, a smaller region in which the iron crystals are arranged in a different orientation than in the surrounding sphere. If this is true, then Earth's heart is like a nested set of shells, with each layer carrying its own record of how the planet cooled, spun, and changed, and with the deepest crystals aligned in their own quiet pattern, distinct from all the iron around them. Deep beneath the inner core boundary, the story of Earth's heart becomes even more intricate. That thin frontier between solid and liquid iron does more than separate two states of matter. It may also act as a kind of archive, quietly recording different stages in the planet's cooling history. As iron freezes onto the inner core, layer after layer. The pattern of crystals and the way they are aligned could preserve a record of how temperature and pressure have changed over billions of years. We cannot visit this boundary, but we can imitate its conditions in miniature. In high-pressure laboratories, scientists squeeze tiny samples of iron and nickel between diamond anvils and heat them with intense lasers, pushing them to pressures of millions of atmospheres and temperatures of many thousands of degrees. Under these extremes, iron does not always form the simple structures we see at the surface. It can adopt unusual arrangements, such as hexagonal, close-packed, or nearly cubic crystals. The shapes and orientations of these crystals strongly affect how seismic waves move through them, hinting that the strange behavior of waves in the deep earth may be rooted in the geometry of iron itself. One of the most puzzling clues from the core is something called anisotropy. More than 3,000 miles below us, seismic waves do not travel the same way in every direction. Waves moving roughly north to south through the inner core tend to arrive faster than waves moving east to west. When geophysicists first noticed this in the 1980s, it was a shock. Why would Earth's iron heart carry vibrations differently depending on direction? The simplest explanation is that the iron crystals inside the inner core are not oriented randomly. Instead, they are lined up in preferred directions, like the grain in a piece of wood. If most crystals are stretched or stacked along Earth's rotation axis, then waves traveling parallel to that axis from pole to pole pass more easily and move faster. Waves crossing the crystals at an angle, such as those going roughly east to west, encounter more resistance and slow down. In this view, the inner core is not just a sphere of metal, but a textured object whose internal grain is shaped by rotation, cooling, and time. As measurements improved, the picture became even more complex. The anisotropy is not the same everywhere. In some regions, the difference between north-south and east-west travel times is strong. In others, it is faint or even reversed. Some studies suggest that the outermost layer of the inner core, just beneath the liquid outer core, has relatively weak anisotropy, while deeper regions are more strongly textured. This hints that the oldest parts of the inner core, formed long ago, may have a different crystal fabric from the newer layers forming today. In that way, wave speeds become a kind of time log, like growth rings inside a tree, encoding when and how the core solidified. There are also small, localized patches where seismic waves speed up or slow down more abruptly than the global pattern would predict. These could be places where turbulence in the liquid outer core has disturbed crystallization at the boundary, leaving behind zones of differently aligned crystals. In this sense, anisotropy is not only a property of the inner core itself, but also a frozen memory of its ongoing conversation with the fluid metal above. Some computer models suggest that changes in the inner core's rotation rate, the same superrotation hinted at by seismic studies, could gradually rearrange the alignment of crystals and strengthen or weaken anisotropy in different regions over time. Another intriguing pattern emerges when scientists look at the inner core as a whole. Seismic waves traveling through the eastern half, roughly beneath Asia and the Western Pacific, tend to move faster and more smoothly than those crossing the western half beneath the Americas and the Atlantic. It is as if one hemisphere of the inner core is more neatly crystallized, while the other is rougher and more disordered. This large-scale contrast is often called the hemispheric puzzle. One way to understand it is to imagine that the inner core is growing unevenly. Iron from the liquid outer core freezes more quickly on one side than on the other. Over millions of years, this would build a thicker, more organized fabric in one hemisphere and a younger, less ordered texture in the opposite half. What could make one side grow faster? The answer may lie above, in the mantle and outer core. The mantle is not uniform. It has cooler regions where subducted slabs sink and hotter zones where plumes rise. If the mantle above one side of the core draws heat away more efficiently, it could encourage iron to solidify there first. Meanwhile, a warmer mantle above the other side would slow cooling and keep the outer core liquid longer. In that way, the slow dance of continents and slabs at the surface might guide crystallization at the very center of the planet. Flows in the outer core may add another layer to this feedback. If currents of liquid metal are stronger or more organized in one hemisphere, they can carry heat and light elements differently across the inner core boundary, reinforcing uneven growth. Over geological time, this could produce mechanical stresses, tilting crystal alignments and contributing to the anisotropy patterns we see. A slightly lopsided inner core could also influence the geodynamo, injecting small irregularities into the outer core's convection and helping to explain why Earth's magnetic field has shifted, weakened, and reversed so many times. All of these structures depend on one simple fact: the core is still hot. For most people, it is tempting to picture the center of Earth as a single glowing sphere, hot simply because it started that way. In reality, scientists have spent decades trying to understand what keeps it so warm. The sun powers life and weather from the outside, but inside, another energy system is at work. That hidden heat keeps part of the core liquid, drives convection, and sustains the geodynamo. For a long time, researchers thought most of this internal heat came from two sources: leftover energy from Earth's formation and the gradual release of heat as the core cools and iron solidifies onto the inner core. More recent work suggests a third important contributor: radioactive decay. Tiny amounts of radioactive elements buried deep inside the planet behave like countless miniature furnaces, releasing heat as their atoms slowly break apart. The main candidates are isotopes of potassium, thorium, and uranium. They are rare compared with iron and nickel, but even trace amounts can release significant energy over billions of years. Near the surface, we see their influence in volcanic activity and geothermal areas. Detecting their presence in the core is much more difficult. Instead of direct samples, scientists rely on subtle clues such as the ratios of helium isotopes in volcanic gases and the detection of ghostly particles called geoneutrinos produced by radioactive decay. Some hot plumes that rise beneath places like Hawaii and Iceland carry chemical signatures that seem to link them to deep, long-lived reservoirs rich in these elements. If radioactive elements are present in the core, they help solve a long-standing puzzle. Simple cooling calculations predict that the core should have solidified more than it has by now. A steady trickle of radioactive heat would slow this freezing, keeping much of the outer core molten and convection vigorous. That extra warmth would be essential for maintaining the geodynamo, and with it, Earth's magnetic shield. Uneven concentrations of radioactive elements could even contribute to the hemispheric puzzle, warming some regions of the core more than others, and subtly influencing where the inner core grows fastest. Alongside heat, composition adds another layer of mystery. When researchers calculate how dense the core should be, if it were made of pure iron and nickel, they find a mismatch. seismic waves move more slowly than expected, and the overall density is lower. The simplest explanation is that lighter elements are mixed into the metal, making the core less dense than a pure iron sphere. This is known as the light element mystery. Several candidates have been proposed, each with its own story. Sulfur bonds readily with iron and was plentiful in the early solar system, making it a natural suspect. Oxygen can dissolve into molten iron under extreme pressures and might have been dragged into the core during the planet's violent youth. Carbon, too, dissolves in iron and could be present in amounts large enough to rival all the carbon stored in Earth's surface, rocks, and oceans. Silicon appears to mix well with iron at core pressures, and tiny amounts of hydrogen, perhaps delivered by water-rich bodies in the early solar system, cannot be completely ruled out. High-pressure experiments and computer simulations show that mixtures of iron with silicon, oxygen, or carbon can reproduce the densities and wave speeds we observe. Seismic data hint that the outer core may contain a different blend of light elements than the inner core, suggesting a layered interior where composition changes with depth. As iron freezes onto the inner core, it tends to push lighter elements back into the outer core, enhancing buoyancy and helping to drive convection. Without these light elements, the outer core might be less able to circulate, and the dynamo might be weaker or shorter-lived. The exact recipe remains uncertain, but the consequences are profound. The types and amounts of light elements in the core carry clues about the conditions under which Earth formed. A core rich in silicon, for example, would hint that the young planet accreted material from a relatively oxygen-poor region of the solar nebula. A core richer in oxygen would paint a different picture, one in which Earth's building blocks were more oxidized. In that sense, the chemistry of the deep core is a fossil record of the solar system's earliest days, written not in stone at the surface but in alloys hidden thousands of miles down, where they quietly shape the magnetic field and the long, slow evolution of our living world. Far beneath the mantle, where solid rock leans against liquid metal, the boundary between them is not a smooth and gentle line. Around 1,800 miles below our feet, seismic images reveal something far stranger. A hidden landscape where mountains rise taller than anything on the surface, crowding the edge of the core in endless darkness. We learned of these buried ranges the same way we learned of the core itself, by listening to earthquakes. When an earthquake sends waves through the planet, some of those waves bounce off the boundary between the mantle and the outer core. If that boundary were perfectly flat, the echoes would come back in simple, predictable ways. Instead, seismologists see tiny delays, extra reflections, and odd distortions that only make sense if the rock above the core is rumpled and uneven. By piecing together many such signals, they have mapped vast ridges and plateaus that seem to rise tens of miles high, dwarfing any surface mountain and stretching for thousands of miles. One leading idea is that these structures are made from ancient, dense rock that has slowly sunk to the base of the mantle. Over billions of years, pieces of ocean floor and fragments of old continents have descended at subduction zones, carrying chemically distinct material downward rather than disappearing. Some of this material may accumulate and pile up at the very bottom, forming rough highlands at the core mantle boundary. In that sense, the mountains beneath us could be graveyards of continents made from the compressed remains of long-vanished oceans and plates. Another possibility is that these peaks record chemistry as well as motion. The contrast between the solid mantle and the liquid outer core is extreme. In some regions, iron from the core may seep upward into the overlying rock, making it heavier and denser. In others, lighter elements from the mantle may sink and spread into layers close to the core. Over time, these exchanges could sculpt highs and lows, carving a jagged landscape where metal and rock have quietly traded material for ages. Compared with this hidden terrain, the surface ranges we know are delicate wrinkles. Seismic studies hint that some core mantle mountains may be 5 times taller than Mount Everest. If we could strip away Earth's outer layers and look directly at this deep boundary, we would see a raw, alien panorama. Towering ridges, broad plateaus, and deep basins wrapped around the entire globe. These mountains are not just scenery. They may help guide the planet's deep circulation. Hot plumes of mantle rock, which rise from near the core and feed volcanic hotspots like Hawaii and Iceland, seem to originate close to the roughest parts of the core mantle boundary. The buried mountains may act like anchors or launch ramps, focusing heat and directing plumes upward. In that way, the shape of the deep landscape could help decide where volcanoes eventually appear at the surface. The uneven terrain may also influence the slow drift of continents. Where the boundary is rough, heat and material can flow differently than in smoother regions, affecting convection in the mantle above. The plates we see moving at the surface may, in part, be responding to the contours of a hidden, mountainous world nearly 2,000 miles below. Three-dimensional seismic imaging has shown that this deep landscape is patchy. Beneath some parts of the Pacific, the boundary appears especially rugged, while under other regions it looks comparatively smooth. This suggests that the core mantle frontier is constantly shaped by local processes such as subducting slabs, piling up, and plumes rising out. It is still unclear whether these mountains are ancient structures that have barely changed or shifting features that slowly rebuild themselves as Earth recycles its outer shell. Many scientists suspect they evolve over time, growing and reforming as new material arrives from above. In some places, volcanic rocks brought to the surface carry strange isotopic signatures, as though their source had been isolated from the rest of the mantle for billions of years. These chemical fingerprints hint that parts of the core mantle boundary act as long-term storage vaults, holding deep reservoirs of ancient material. If so, the mountains at the base of the mantle are not just piles of rock. They are archives of Earth's early history. Scattered among this rugged terrain are even stranger features. Thin patches where seismic waves suddenly slow almost to a crawl. These are called ultra-low velocity zones, and they lie directly above the outer core. They are only tens of miles thick, but their effect on earthquake waves is dramatic. When seismic waves pass through them, their speeds can drop by as much as 30%, as if the waves have struck pockets of something softer and denser than the surrounding mantle. One idea is that they are regions of partially molten rock, made from leftovers of the global magma ocean that once covered the young Earth. As that fiery ocean cooled, most of it solidified into the mantle we know, but some especially dense, iron-rich melt may have sunk and become trapped near the core. Billions of years later, those ancient residues could survive as thin layers, fossils of Earth's earliest molten days. Another possibility is that ultra-low velocity zones are places where the mantle has mixed with more iron from the core, creating rock that is both chemically unusual and very slow to transmit waves. Some scientists have even suggested that they may contain remnants of the giant impact that formed the moon when a Mars-sized body is thought to have collided with the early Earth and left behind odd blends of metal and rock at depth. Whatever their origin, these patches appear to be deeply involved in Earth's dynamics. Ultra-low velocity zones are often found at the base of mantle plumes, as if they serve as hot, dense launch pads from which plumes rise. Some beneath the Pacific and beneath Africa are enormous, stretching hundreds of miles across. From these regions, heat and chemically distinctive material may feed volcanoes at the surface for tens of millions of years. Because ultra-low velocity zones are so thin and so deep, they are hard to see clearly. Instead of simple images, scientists look for subtle echoes and scattered waves to infer their presence. As global networks of seismometers grow and methods improve, those fuzzy blobs are slowly sharpening into more detailed shapes. It is becoming clear that not all ultra-low velocity zones are alike. Some show signs of partial melt, almost like tiny hidden lava ponds. Others appear solid, but chemically exotic, with compositions unlike typical mantle rock. They gather especially around the edges of huge, slow regions in the lowermost mantle, suggesting they may help define where the largest plumes begin. Those vast, slow regions are another of Earth's deep enigmas. Just above the core, under Africa and under the Pacific, seismic waves move unusually slowly through gigantic blobs of mantle material that span thousands of miles. These are called large, low shear velocity provinces, but many people simply call them giant core structures. They are roughly the size of continents, reaching hundreds of miles high, and they may have been part of Earth's interior for billions of years. The rock inside these provinces seems hotter and somewhat different in composition from the surrounding mantle. One idea is that they are made from chemically distinct material left over from the early magma ocean, which crystallized and sank to the base of the mantle. Another is that they are built from the long accumulation of subducted slabs, oceanic crust, and sediments that have piled up at the bottom over immense spans of time. A third possibility is that they contain fragments of the impactor that helped form the moon, preserved as foreign matter deep within Earth. Whatever their origin, these giant structures appear to act as hubs in the planet's interior circulation. Many mantle plumes seem to arise from their edges, as if heat and buoyant material collect along their boundaries before rising toward the surface. The location of powerful hotspots such as Hawaii, Iceland, and some Pacific island chains lines up with the projected edges of these blobs. In this way, the deep core structures may help decide where some of Earth's most persistent volcanoes take root. They may also shape the life cycle of continents. Some geologists think that the upwellings from these deep provinces have helped break apart ancient supercontinents and guided where new oceans opened. Over hundreds of millions of years, continents may drift, cluster, and split above these hidden giants, responding to the slow breathing of the mantle below. Lava from certain hotspots carries chemical signatures that look as though they come from reservoirs, isolated for billions of years. That has led many researchers to suspect that these giant structures are long-term storage zones, keeping ancient materials sealed away near the core mantle boundary. They might be among the oldest surviving pieces of Earth, still influencing volcanism and convection today. It is not yet clear whether these blobs are fixed pillars or slowly drifting masses. Some models suggest they can move, merge, or split over geologic time, like massive drops of thick fluid. Others see them as relatively stable, anchored by their own density at the base of the mantle. The structure beneath Africa, in particular, appears taller and perhaps less stable than the one beneath the Pacific, which may help explain why the African region hosts so much rifting and unusual volcanic activity. Together, the mountains, ultra-low velocity zones, and giant core structures paint a picture of the core mantle boundary, not as a flat dividing line, but as a complex, shifting borderland, a place where ancient material collects, new plumes are born, and the deep engine of Earth expresses some of its most dramatic patterns. All of this deep structure ties back to one quiet effect that reaches us at the surface: Earth's magnetism. The same flows of liquid metal that respond to heat from below and to the shape of the boundary above also generate the magnetic field that wraps our planet. The geodynamo lives in the outer core, where molten iron and nickel move and twist under the influence of rotation. As they flow, they carry electric charges and build a magnetic field that loops far into space. We know from ancient minerals that this field has existed for more than 3.5 billion years, guiding compasses in more recent history and shielding life long before anyone could measure it. Its persistence means that Earth has somehow maintained the delicate balance of heat and motion needed to keep the dynamo running. The growth of the inner core, the presence of light and radioactive elements, and the complex boundary conditions at the base of the mantle all help keep the core active. The field itself flickers and shifts. The magnetic poles wander and sometimes trade places. Regions like the South Atlantic anomaly mark where the field grows unusually weak and space radiation brushes closer to the atmosphere. Yet despite these changes, the shield endures. Other worlds have not been so fortunate. Mars and the Moon lost their global fields long ago as their interiors cooled and quieted. Venus, though similar to Earth in size, has no strong magnetic shield at all. Jupiter and Saturn boast enormous fields, powered by exotic forms of matter. But among the rocky planets, Earth's long-lived magnetism remains unusual, held together by hidden motions thousands of miles below our feet. Far out in the solar system, other worlds carry their own stories of magnetism and loss. Comparing them with our own helps scientists understand why Earth's inner engine has stayed active and kind to life, while others never started or faded away. Against that quiet comparison, Earth's magnetic field shows another of its stranger habits. Sometimes it turns inside out. Most of the time, every compass on the planet more or less agrees on where north is. Yet, over long stretches of time, Earth's magnetic poles have wandered and, many times, have completely switched places. These events are called magnetic reversals. North becomes south, and south becomes north. They unfold slowly over thousands of years, but their fingerprints are written into rocks, into the seafloor, and even into the subtle ways the atmosphere reacts to incoming radiation. The clearest evidence comes from cooling lava. When molten rock rises and spills out at the surface, the iron-rich minerals inside act like tiny compasses. As the lava cools and solidifies, those minerals lock in the direction of the magnetic field at that moment. By sampling ancient volcanic rocks across many continents, scientists found that some flows preserve a field pointing roughly like today's, while others record a field flipped the other way. What we now call the North Magnetic Pole has, many times, pointed toward geographic south. The ocean floor carries an even more striking record. Along mid-ocean ridges, new crust is born as magma wells up and freezes. As it does, it captures the direction of the field. Over millions of years, this process has produced long stripes of seafloor with alternating magnetic polarities laid out on either side of the ridges like a barcode. Reading those stripes reveals a history of many reversals going back hundreds of millions of years. The last full flip, known to geologists as the Brunhes-Matuyama reversal, happened about 780,000 years ago. Before that, reversals came at irregular intervals. Sometimes they occurred roughly every couple of 100,000 years. At other times, the field held its orientation for tens of millions of years. During a long stretch in the Cretaceous period, for example, the field stayed in the same direction for nearly 40 million years before it began flipping again. This uneven pattern tells us that reversals are not clockwork events, but outcomes of chaotic changes in the core. Deep in the outer core, the geodynamo is constantly steered by turbulent flows of liquid metal. Computer simulations that mimic these flows show that a reversal can happen when the pattern of motion becomes especially tangled. The main dipole field weakens, patches of opposite polarity grow and merge, and eventually, the large-scale field reestablishes itself, pointing the other way. It is a bit like watching a complex whirlpool. Most of the time, it spins one way, but under the right conditions, eddies disrupt it enough that it stalls and begins turning in the opposite direction. A reversal does not happen overnight. The field gradually weakens, sometimes to a fraction of its usual strength, and becomes more complicated. Instead of one clear north-south axis, there may be several temporary poles scattered around the globe. Compasses, if anyone had been there to use them, would have behaved erratically, swinging toward shifting clusters of magnetic influence. Eventually, the field strengthens again, now oriented the opposite way. While the magnetic shield is weaker, more charged particles from the sun and from deep space can reach the upper atmosphere. The magnetosphere still deflects much of this radiation, and the air itself provides a second layer of protection, so life on the ground remains largely safe. But the increased particle flux leaves traces. During past reversals and near reversals, levels of certain isotopes, such as beryllium-10, rose in ice cores and sediments, marking times when more energetic particles reached the atmosphere. Auroras would likely have been more frequent and spread to much lower latitudes, lighting skies that today rarely see them. Sometimes the field seems to begin a reversal and then change its mind. These shorter episodes are called geomagnetic excursions. One of the best known is the Lassonde event. About 41,000 years ago, for a few centuries, the field weakened sharply and the poles wandered far from their usual positions, drawing closer to the equator. Before the system recovered and the field returned to its previous orientation, radiation at Earth's surface increased, but there is no sign of a global biological catastrophe. Life appears to have adapted, as it has through many quiet changes in the field. Today, the magnetic field is again shifting in complex ways. The North Magnetic Pole is wandering quickly across the Arctic, and a broad region of unusual weakness, called the South Atlantic Anomaly, stretches from South America across the southern Atlantic toward Africa. In that zone, the magnetic field at satellite altitudes is significantly weaker than average, allowing more charged particles to dip closer to Earth. Instruments aboard spacecraft can malfunction there, so some satellites are powered down when they pass overhead. Over the past 2 centuries or so, the global field has weakened by roughly 10%, while the South Atlantic anomaly has deepened and expanded. Its weakest point drifts westward, moving tens of kilometers each year. Whether these changes are early hints of a coming reversal or simply part of the normal wobble of a restless dynamo is still unknown. Geological records show that the field has weakened and recovered many times without fully flipping. Whatever path the field takes, the deeper story lies in how we know any of this at all. We will never send a drill bit to the core, the deepest hole humans have ever dug. The Kola super deep borehole in Russia reaches only about 7.5 miles into the crust, a tiny fraction of the distance to Earth's center. To explore farther, we rely on Earth's own quakes. Each time a strong earthquake shakes the planet, it sends out seismic waves that race through the interior. Some compress and expand material in the direction they travel. Others shear it side to side. The first kind, often called primary waves, can travel through solids, liquids, and gases. The second kind, secondary waves, can move only through solids. That simple difference revealed one of Earth's greatest secrets. Secondary waves vanish when they reach the outer core, so we know that layer must be liquid. Primary waves slow and bend as they enter and cross the core, telling us about its density and structure. By comparing when these waves arrive at thousands of seismometers around the world, scientists can reconstruct the paths they took. Over decades, as global networks grew, patterns emerged. Some regions deep inside Earth bend waves more strongly than expected. Others slow them down or let them pass unusually fast. From these variations, geophysicists have mapped not only the broad outlines of a liquid outer core and solid inner core, but also finer features such as the inner core, anisotropy in crystal alignment, ultra-low velocity zones, and the giant structures at the base of the mantle. The discovery of the solid inner core itself came from such careful listening. In the 1930s, Inge Lehmann noticed faint echoes of primary waves arriving at times that suggested they had reflected from a boundary deep inside the core. Her interpretation, that Earth holds a solid metal sphere surrounded by liquid metal, reshaped our understanding of the whole planet. Modern seismic tomography works much like a medical scan, using many paths and many quakes to build three-dimensional images of the unseen. Even with these maps, some questions can only be answered by recreating core conditions in the laboratory. Alongside slow, steady compression in diamond anvil cells, scientists use shockwave experiments to briefly lift materials to pressures and temperatures like those thousands of miles below. In these tests, a sudden impact or a burst of laser light sends a compression wave racing through a small metal sample, pushing it to pressures millions of times higher than the air at sea level and heating it to thousands of degrees Celsius. At facilities such as the National Ignition Facility in California, hundreds of laser beams can focus their energy on a target smaller than a fingernail, delivering more than 1 million joules of energy in a tiny fraction of a second. For a few billionths of a second, the sample is squeezed and heated to conditions comparable to those near the boundary between the outer and inner core. In that brief window, scientists can measure how sound waves move through the material, how dense it becomes, and whether it stays solid or melts. These experiments have narrowed the range of possible temperatures inside Earth. For many years, Estimates for the core spanned from about 4,000 to 7,000 degrees Celsius. Shockwave measurements on iron and iron alloys under core-like pressures point toward values near the higher end, suggesting that the inner core may be nearly as hot as the surface of the Sunday. That temperature, in turn, affects how fast Earth cools and how long the geodynamo can keep running. Shock experiments also help with the puzzle of light elements mixed into the core. Seismic waves tell us that the outer core is less dense than pure iron would be. By shocking alloys of iron with small amounts of elements such as silicon, oxygen, carbon, or sulfur, scientists can see which mixtures best match the observed densities and wave speeds. The results suggest that combinations of these light elements could account for the missing density, supporting the idea of a chemically layered core. Under core pressures, even the crystal structure of iron changes. At the surface, iron can adopt several arrangements of atoms deep inside Earth. Experiments show that it prefers tightly packed structures, often hexagonal, and may, under some conditions, shift toward body-centered cubic forms. These details matter because they influence how seismic waves travel through the inner core and may help explain why waves move faster in some directions than in others. Shockwave methods do not rely only on lasers. Gas guns can fire projectiles at high speed into metal samples, generating shock waves that reach deep earth pressures, though at slightly lower temperatures than laser shots. Carefully controlled explosive charges have also been used to compress larger samples for longer moments. Each technique offers a different view of how materials behave under extreme stress, and together they fill in pieces of the puzzle. New generations of ultra-fast X-ray sources make it possible to watch these changes almost in real time. At powerful facilities, pulses of X-rays, only trillionths of a second long, can capture snapshots of a material as a shock wave passes through it, revealing how atomic structures shift and rearrange. This window into the behavior of matter at extreme conditions does more than illuminate Earth's own core. The same physics applies to the interiors of other planets, and even to the metallic hydrogen thought to exist inside gas giants like Jupiter and Saturn. By understanding how matter responds to crushing pressure and intense heat, we learn not only about the deep heart of our own world, but also about the hidden cores of many others, drifting silently through the dark. Deep inside the planet, one question has quietly followed scientists for more than a century. Just how hot is Earth's heart? It sounds simple, but no thermometer could ever survive those depths. Instead, the answer has to be stitched together from clues: the way heat escapes through the surface, how seismic waves move, and how tiny samples of iron behave when they are squeezed and heated in laboratories. Earth is constantly losing heat to space. Some of that warmth comes from the crust and mantle, but a large share is thought to rise from the core. By measuring the total heat flowing out through the surface and comparing it with what rocks alone can supply, researchers can estimate how much must be coming from below, and therefore how hot the deep interior must be to drive that flow. Early calculations suggested a core temperature of around 4,000 degrees Celsius, hot enough to keep iron molten, but cooler than many modern estimates. Seismic waves added another layer of constraint. The stiffness of the inner core tells us it is solid iron or an iron alloy, yet the speeds of the waves that pass through it hint that it sits very close to its own melting point at those pressures. That implies a temperature much higher than 4,000 degrees Celsius nudging models toward a core that is balanced on the edge between solid and liquid. To explore that edge, scientists use diamond anvil cells and shockwave experiments, recreating, for fleeting instants, the pressures found thousands of miles down. When tiny samples of iron are squeezed between diamonds and heated with lasers or slammed with shock waves, they reveal when they melt and how their atoms arrange themselves. These tests suggest that under core conditions, iron melts at temperatures between roughly 6,000 and 7,000 degrees Celsius, nearly as hot as the visible surface of the Sunday. In that picture, the outer core would be a metallic ocean at similar temperatures, while the inner core, though just as hot, is held in solid form by the immense pressure. Even so, different experiments do not always give the same number. It is extraordinarily difficult to keep such extreme conditions steady, even for a fraction of a second. Small differences in method can lead to meaningful disagreements. The picture is complicated further by the fact that Earth's core is not pure iron. Seismic data show it must contain lighter elements, perhaps carbon, oxygen, silicon, or sulfur in smaller amounts. These ingredients can lower the melting point of iron alloys by hundreds of degrees. The estimated temperature of the core shifts depending on which mixture is assumed. The exact value matters because it shapes almost everything else in the deep Earth. The geodynamo that powers the magnetic field depends on heat flowing out of the core into the mantle. If the core is relatively cool, convection slows and the field may weaken. If it is hotter, convection is more vigorous and the field stays strong. Core temperature also controls how quickly the inner core grows as liquid metal in the outer core freezes onto its surface, releasing heat and light elements that stir the dynamo. A hotter, more sunlight core temperature would point to a younger inner core, perhaps only about 1 billion years old. A cooler core would allow it to be older. New tools are gradually tightening the estimates. Tiny ghost-like particles called geoneutrinos, produced when radioactive elements decay inside Earth, help constrain how much heat comes from the crust and mantle and how much must arise deeper down. Measurements of helium and other gases in volcanic plumes hint at conditions near the core mantle boundary. Synchrotron X-ray studies, where intense beams of X-rays probe iron alloys under pressure, are refining our understanding of how iron's crystal structure shifts at depth. Together, these lines of evidence tend to favor a hotter core, closer to the higher end of past estimates, and a planet whose heart is still fiercely warm. Wrapped around that heart is another mystery: its age. The solid inner core lies more than 3,000 kilometers beneath us and spans roughly 1,500 miles, but we do not yet know exactly when it began to crystallize. Did the solid sphere appear almost 4 billion years ago, early in Earth's history? Or is it a more recent feature, perhaps less than 1 billion years old? The answer would reshape our view of how the planet cooled, how long its magnetic field has been stable, and when conditions became truly favorable for long-term life. Because the core cannot be sampled directly, its age must be inferred from indirect clues. One of the most important is Earth's magnetic history. The dynamo in the outer core has been generating a field for at least 3.5 billion years, as shown by tiny magnetic minerals in very ancient rocks. Some paleomagnetic studies suggest that around 1 billion years ago, the field suddenly became stronger and more stable. That could mark the time when the inner core began to grow, adding a new source of energy as iron crystallization released heat and light elements into the outer core. Seismic anisotropy offers another hint. Waves travel faster through the inner core from north to south than from east to west, suggesting that iron crystals have slowly aligned in preferred directions. Some models say that to produce the observed pattern, the inner core would need billions of years of growth. Others argue that, under the right conditions, alignment could develop more quickly, consistent with a younger core. Heat flow is at the center of the debate. Experiments on iron under core pressures suggest that it may conduct heat very efficiently. If that is true, Earth would lose energy faster, and the core would have cooled enough to begin crystallizing only relatively recently. In that case, mechanisms other than inner core growth, such as chemical convection driven by compositional differences or strong cooling from the overlying mantle, must have powered the early dynamo. Some studies of seismic wave paths even hint at a tiny inner core at the very center, with a crystal fabric different from the surrounding region. That pattern could reflect a two-stage history. An older seed formed long ago, wrapped in younger layers that grew more rapidly in the last billion years. Hints about Earth's earliest interior also arrive in a lighter, more elusive form: helium. Most of the helium we encounter at the surface is helium-4, produced by radioactive decay in rocks. Helium-3, by contrast, is thought to be largely primordial, left over from the cloud of gas that formed the sun and planets. It is extremely rare and chemically shy, more likely to slip through than to bond. When helium-3 appears in gas from volcanic vents, it is a whisper from deep inside the planet. Certain hotspots, such as Hawaii and Iceland, release gases with unusually high ratios of helium-3 to helium-4. Those signatures suggest that the plumes feeding these volcanoes tap reservoirs that have remained isolated since Earth's early days, perhaps near the core mantle boundary. Some recent measurements, including very high helium-3 levels in basalt from Baffin Island, have led researchers to propose that at least part of this primordial gas may come from regions close to the core itself. If so, it would mean that pockets of Earth's deep interior have stayed remarkably untouched for billions of years, preserving a tiny sample of the original solar nebula. The slow leak of helium-3 into the atmosphere, only on the order of a few kilograms each year, suggests that large amounts remain trapped inside. Comparing helium-3 with other noble gases, like neon and argon, helps distinguish between truly ancient sources and material that has been recycled through the crust. Taken together, these gases act like tracers, outlining hidden pathways from the deep earth to the surface. All of these threads, core temperature, age, composition, and trapped gases, feed into one larger, quiet question: how long will Earth's magnetic heart keep beating? The geodynamo depends on movement in the outer core. At the moment, that motion is driven by two main processes working together. As the core cools, heat escapes upward into the mantle, making regions of liquid metal buoyant and setting them in motion. At the same time, as iron freezes onto the inner core, it releases both heat and lighter elements, such as oxygen or sulfur, into the outer core, adding another push to convection. Earth's rotation then shapes these flows into spirals, and the spirals sustain the field. As long as enough energy is available, the dynamo should continue. Earth currently loses on the order of tens of terawatts of heat to space. If cooling proceeds at roughly its present rate, there may be fuel for the magnetic engine for at least another billion years, perhaps longer. But if the core conducts heat more efficiently than we think, it could cool and stratify more quickly, reducing convection and eventually allowing the outer core to freeze from the inside out. In that distant scenario, the field would weaken, flicker, and one day fail. There are signs that the field is already in a restless phase. Over the past 2 centuries, its overall strength has dropped by about 10%, and the South Atlantic anomaly has grown as a persistent weak spot. The magnetic poles wander more quickly than they did in the past. Paleomagnetic records, though, show that the field has gone through many such episodes, periods of weakness and rapid change, followed by recovery and long stretches of stability. Reversals and near reversals may be part of the way the dynamo adjusts to shifting patterns of heat, flow, and composition inside the core. Farther out in the solar system, other worlds offer a glimpse of different endings. Mars likely once had its own dynamo, which faded as the small planet cooled and its core quieted. Without a global magnetic shield, much of its atmosphere was peeled away by the solar wind, leaving behind a thin sky and a cold, exposed surface. For now, Earth is still wrapped in a strong, flickering field, its hidden engine deep below our feet, turning slowly in the dark, holding back space just enough for oceans, air, and life to endure. Far away, close to the sun, a small world offers a reminder that Earth's inner engine is not guaranteed. Mercury is much smaller than Earth, yet it still clings to a weak magnetic field, perhaps kept alive by unusual sulfur-rich chemistry in its core and a thin layer of liquid metal that is not yet completely stilled across the solar system. Each rocky planet carries its own version of the deep story. Size, heat, composition, and rotation all have to line up just right for a geodynamo to arise and endure. Earth is one of the few that found that balance and kept it. When we compare Earth and Mars, the contrast is particularly poignant. Both are rocky planets born from the same cloud of dust and gas about 4.5 billion years ago. Yet today, one is blue and warm, wrapped in oceans and forests under a thick, protective sky. The other is cold, dry, and thinly veiled by a fragile atmosphere that struggles to hold on against the Sunday. The difference begins deep inside. Earth still has a hot, moving core that drives a strong magnetic field. Mars, by contrast, appears to have let its dynamo fade. Ancient river valleys, deltas, and lake beds on Mars tell us it once had flowing water, and perhaps even wide seas. To keep liquid water at the surface, it must have owned a thicker atmosphere and a climate that could stay warm. That, in turn, suggests it once had a magnetic shield not so different from Earth's, a field that guarded its air from being stripped away. Somewhere around 4 billion years ago, that shield failed. The Martian dynamo went quiet. Without a strong magnetic field, the solar wind slowly peeled away much of the atmosphere. Over long spans of time, water at the surface vanished into space or retreated into ice and hidden reservoirs. Mars did not freeze instantly. It faded, becoming the stark desert we see now. One key reason lies in size. Earth's radius is nearly twice that of Mars. That extra mass allowed Earth to retain heat much longer, keeping its outer core molten and convecting. Mars, being smaller, radiated its internal heat more quickly. Its outer core may have solidified early or become stratified with a stable, unmoving layer at the top that choked off vigorous convection. Without that churning, the dynamo could not survive. Even if some molten metal remains, chemistry probably contributed too. Studies suggest that Mars's core may be rich in sulfur, which lowers the melting point of iron. That might have kept parts of the core liquid for a time, but not necessarily moving in the right way. As the planet cooled further, motion slowed, then stalled. Earth's core, in contrast, seems to contain a blend of lighter elements: oxygen, silicon, sulfur, that, together with the steady growth of the solid inner core, keep convection lively. The difference ripples outward. Earth's magnetic shield helped preserve its atmosphere and oceans, creating a long, stable window for life to emerge and evolve. Mars, losing its shield early, lost much of its surface water as well. Traces of ice linger at the poles and in the subsurface, but the era of lakes and rivers on the Martian surface has long passed. Looking at Mars is a little like peeking into Earth's distant future, a reminder that a dynamo can die, and a warning that our own protective field is not eternal. It also nudges a quieter question. What if Mars had held on a little longer? If its core had kept convecting, its field might have protected a thick atmosphere for hundreds of millions of additional years. In that window, simple life might have taken hold, just as it did on Earth around 3.5 billion years ago. Rovers and landers now roam its ancient rocks, searching for faint chemical traces that might confirm that, for a short time, Mars too was alive. Deeper still, inside Earth, the core itself seems to have its own kind of restlessness. Not all quakes happen in brittle crust. Some hints point to subtle shifts thousands of miles down in the solid inner core. These possible core quakes are not like the sharp jolts that topple buildings. Instead, they are inferred from tiny changes in how seismic waves travel through the very center of the planet. When a large earthquake shakes the surface, its waves pass through the whole globe, including the core. Instruments around the world record their arrival times. Most of the time, the patterns match what we expect for a solid inner core and a liquid outer core, but every so often, waves that traveled through the deep core arrive just a little earlier or later than predicted, or they show subtle changes if the same path is sampled decades apart. These small anomalies suggest that something inside the inner core may have shifted. It is hard to imagine a solid ball of iron under such crushing pressure, breaking in the way crustal rocks do. A gentler picture is that iron crystals in the inner core slowly grow and rearrange under stress. As they change shape or orientation, they can release stored stress in small bursts. At the surface of a frozen pond, expanding ice sometimes cracks with sudden, echoing pops. In the inner core, a similar process might play out at pressures millions of times greater, with metallic crystals slipping and realigning in slow, powerful whispers. In 2018, one study reported evidence of a sudden change in how waves pass through the inner core, as if some internal reorganization had occurred that left a lasting mark. The result is still debated, but it hints that the inner core is not a perfectly uniform, everlasting sphere. It may be more like a slowly shifting, iron-rich world of its own, with stress building and easing in rhythms we are only beginning to sense. If such deep events do occur, they might be connected, however delicately, to the flows in the liquid outer core and the behavior of the magnetic field. A small, structural shift in the inner core could subtly alter how heat and light elements leave its surface, nudging convection patterns and perhaps contributing to the slow drift of magnetic poles or to small irregularities in the field. For now, that connection remains an intriguing idea rather than a solid conclusion. As scientists listen more carefully to Earth's vibrations, they have also begun to imagine that the core might host states of matter that stretch our everyday experience. High-pressure experiments and computer simulations point to possibilities that sound almost fantastical but are grounded in physics pushed to its limits. One idea is that, in some deep layers, hydrogen might enter a superionic state. In such a state, the heavier atoms, perhaps oxygen or iron, form a more or less rigid framework, while hydrogen ions move freely through it, as if a liquid were flowing inside a solid. Laboratory experiments have already created superionic water under conditions similar to those inside ice giants like Neptune. Some researchers wonder whether a thin zone of superionic hydrogen or other light elements could exist near Earth's core mantle boundary, altering how heat and electricity move across that interface. Another concept is iron snow. Rather than a perfectly uniform ocean of molten metal, the upper part of the outer core might be a region where small iron crystals continually form, grow heavy, and gently fall like metallic snowflakes. As these crystals sink toward the inner core, they release heat and leave lighter elements behind in the fluid above. That process would add another source of buoyancy, stirring the outer core and helping to power the dynamo. The mixture of lighter elements in the core, carbon, silicon, sulfur, oxygen, perhaps even traces of hydrogen, may also create exotic compounds that never form near the surface. Under pressures millions of times higher than atmospheric pressure, their atoms can settle into unusual crystal patterns. These unfamiliar structures could help explain why seismic waves slow or speed up in certain regions, or why parts of the inner core appear softer or more irregular than expected. Some seismic images suggest pockets inside the inner core where waves move more slowly, hinting that those regions might be warmer, more disordered, or even partly molten compared with their surroundings. If that is true, the inner core may not be a single, perfectly solid ball at all, but a mosaic of firmer and softer patches, solid and semi-solid iron sharing space in Earth's deepest layer. There is also speculation that iron itself could enter a superionic-like state at the extreme temperatures and pressures of the very center, behaving partly like a crystal and partly like a liquid metal, blurring the line between solid and fluid in ways that would change how heat and electricity flow. These ideas are still being tested, but they hint that the core may be stranger than any simple model suggests. As measurements have improved, a finer structure has emerged inside the inner core as well. Seismic waves traveling through its exact center sometimes behave differently from those that skim nearer its outer edge. This has led to the suggestion that there is an inner core at the very heart of the planet, a smaller sphere within the inner core, with its iron crystals aligned in a different direction or arranged in a distinct pattern. If so, that nested structure would mean Earth's iron heart has recorded multiple stages of its own growth, preserving within it a history of anisotropy, uneven crystallization, and perhaps even those exotic states of matter that only appear in the deepest dark. Deep in the story you and I have been following, there is a smaller, quieter secret inside the solid inner core. Some scientists now see hints of an even deeper structure, a core within the core, like a second heart beating inside the first. The first clues came from listening very carefully to seismic waves. For years, geophysicists knew that waves travel faster through the inner core from pole to pole, then along the equator. That anisotropy suggested iron crystals were mostly aligned with Earth's spin axis. But about 2 decades ago, something curious appeared in the data. Waves that passed through the very center of the core behaved slightly differently from those that crossed only the outer part of the inner core, as if they had entered a region with a new texture. In models, this innermost region is often drawn as a sphere, roughly 400 miles across, about half the size of the moon. Near the outer edge of the inner core, waves still move fastest north-south. Deeper in, the direction of fastest travel seems to tilt, no longer lining up with Earth's rotation in the same way. It is as though the iron in the innermost core is arranged in a different pattern from the layers wrapped around it. One way to picture this is as a time capsule. Perhaps when the inner core first began to crystallize, iron solidified in one preferred orientation, or even in a slightly different crystal phase. Later, something changed. The way heat left the core, the speed of Earth's rotation, the mix of light elements in the metal. New layers froze on in a different alignment, building a shell around an older seed. The inner core would then be a fossil from an earlier chapter in Earth's deep history, preserving a snapshot of conditions when the solid core first appeared. Composition could add another twist. If the earliest core material trapped a little more carbon or silicon than the layers that followed, the crystal structure at the very center might differ subtly from the iron-rich shell outside it. That would change how waves move there, and it might help explain why the deepest paths show such delicate, unpredictable variations. Laboratory work supports the idea that iron can adopt more than one crystal structure under core conditions. At those pressures and temperatures, it may favor a tightly packed hexagonal arrangement, but under slightly different conditions, it could flip into a more cubic pattern. If the innermost core formed in one structure and the outer inner core in another, the boundary between them would show up as a faint but real shift in seismic behavior, a tiny discontinuity hidden inside the larger sphere. This layered heart may even mark the turning point in Earth's magnetic life. Some estimates suggest the inner core as a whole is around 1 billion years old. If the innermost region formed first, in a distinct phase, it might coincide with the moment when crystallization began to feed the geodynamo, adding a new source of energy to the magnetic field that still wraps around us. In that sense, the deepest iron could be a record of the first brightening of Earth's long-lived shield. The evidence is still fragile. Only the largest earthquakes send waves strong enough to cross the very center and return. Their signals are faint and easily tangled with noise. Yet study after study has found patterns that point in the same direction. The innermost few hundred miles of the core do not behave exactly like the rest. For now, the inner core remains a careful inference rather than a certainty, but it gently suggests that Earth's heart has its own layered history. From there, the story widens again, out to the time when the core itself was born. When Earth was young, it was not the cool, layered world we know now. About 4.5 billion years ago, the sun formed from a collapsing cloud of gas and dust. The leftover material clumped together into small, rocky bodies that collided and merged, building the early planets. Each impact released enormous amounts of energy, melting much of the growing Earth into a deep, restless ocean of rock and metal. In that molten world, heavier elements such as iron and nickel sank toward the center, while lighter, silicate material floated upward to form the mantle and eventually the crust. This separation, called differentiation, is what gave Earth its onion-like structure, core in the middle, mantle around it, and a thin, changing skin of rock at the top. But exactly how fast the metal drained inward and which elements it carried with it are questions the present-day core is still helping us answer. Some of the sharpest clues come from isotopes, different versions of the same element that act like built-in clocks. The ratios of certain tungsten and hafnium isotopes in very ancient rocks suggest that Earth's core formed astonishingly quickly within the first few tens of millions of years. That speed points to violent events, giant impacts that melted almost everything, allowing metal to plunge inward in great waves. In that storm of collisions, Earth likely swallowed material from other young worlds. Some of their metal may still be locked into the core, buried forever at the planet's center. Even the rare gas helium-3 carries a whisper of those days. This light isotope is thought to be largely primordial, captured from the solar nebula when Earth was still forming. Small amounts leak out today in some volcanic plumes, hinting at reservoirs deep in the mantle, perhaps near the core mantle boundary. If those reservoirs really exist, they mean that parts of Earth's interior have stayed almost untouched since before the planet fully took shape. The inner core, for its part, records the thermal side of the story, how quickly Earth cooled when the center began to freeze, and how heat has escaped through time. If the solid core began forming only about 1 billion years ago, then for most of Earth's history, the entire core would have been liquid. The early dynamo would then have been powered by other sources, radioactive decay, chemical layering, or strong heat flow out of the core until crystallization started to add its own energy. The innermost core, with its distinct alignment, might preserve traces of that transition, a structural memory of the dynamos switching on in a new way. Experiments on metallic alloys lend weight to this picture. By squeezing mixtures of iron, nickel, and light elements to millions of times atmospheric pressure, scientists can see which compounds remain stable and which separate. The results suggest that differentiation may not have been a single, clean event, but a series of episodes, metal sinking, mixing, and separating again as the young planet heated and cooled in bursts. Each episode would have left subtle chemical fingerprints in the core, fingerprints that are still quietly influencing the geodynamo today. All of this might feel far from the shorelines, forests, and cities we know, but the link between the deep core and life is one of the most intimate connections on Earth. The most direct thread runs through the magnetic field. The geodynamo in the liquid outer core generates an invisible shield that extends far into space. It deflects much of the solar wind, the steady stream of charged particles from the sun that would otherwise batter the atmosphere. Without that shield, Earth's air would gradually erode, as happened on Mars, where a once thicker atmosphere was stripped away after its smaller core cooled and its dynamo faded. The magnetosphere does more than hold on to air. It also bends away high-energy particles that could damage living cells. Some of those particles are funneled along field lines into the polar regions, where they collide with atoms in the upper atmosphere and paint the sky with auroras. Those shifting curtains of light are the visible edge of a far larger, protective structure that operates constantly, mostly unseen. The core's heat feeds into another life-sustaining system, plate tectonics. Heat escaping from the core and lower mantle helps drive the slow convection that moves tectonic plates. When plates collide, pull apart, or slide past one another, they build mountains, open oceans, and fuel volcanoes. Over millions of years, this restlessness acts like a planetary thermostat. Volcanic eruptions release carbon dioxide into the atmosphere. Weathering and subduction draw carbon back down into the mantle. Together, these processes help regulate the greenhouse effect, keeping Earth's temperatures within a range where liquid water can persist. Without that deep engine, a planet can drift into extremes. On Venus, which is similar in size to Earth but may lack efficient cooling and plate tectonics, carbon dioxide piled up into a runaway greenhouse, heating the surface to hundreds of degrees Celsius. On Mars, with its small size and faded core, the opposite happened. Heat leaked away, the dynamo shut down, the atmosphere thinned, and water retreated. Even the fluctuations of the magnetic field may have brushed against the story of life. During reversals and near reversals, when the field weakens and changes shape, more cosmic radiation can reach the upper atmosphere. Some researchers have wondered whether these episodes left subtle imprints on evolution, perhaps by slightly increasing mutation rates. The evidence so far is suggestive rather than conclusive, but it reminds us that processes in the core can echo all the way up into biology. Ancient rocks add another quiet note. Some of the oldest minerals on Earth, more than 3 billion years old, carry traces of magnetism frozen in as they formed. Those tiny records show that a global magnetic field already existed when early microbial communities were taking shape. Life and the core seem to have grown old together, the one building complexity at the surface, while the other kept space at bay. Even now, life helps us read the core in indirect ways. Gases rising from deep volcanic plumes, helium-3, neon, xenon, with unusual isotopic ratios, carry signatures of reservoirs that have been hidden near the core mantle boundary since the planet's youth. By measuring those gases with sensitive instruments, geochemists can glimpse the chemistry and history of regions far below, linking breath, rock, and metal in a single chain. When we look outward to other worlds, this partnership between life and the core becomes a guide. Venus, nearly Earth's twin in size, seems to lack a strong magnetic shield and shows no clear signs of plate tectonics. Mars lost its dynamo long ago. Earth sits in a narrow, fortunate place, large enough to hold its heat, active enough to keep its core moving, and dynamic enough to recycle its surface and air. That is why astronomers, when they search for habitable exoplanets, do not only ask whether a world orbits at the right distance from its star, they also wonder what lies at its center. Is there a molten, convecting core? Could a magnetic field arise and survive? Oceans and air, it seems, may not be enough by themselves. Without an active heart of metal, even a beautiful blue world might one day lose its sky. In that quiet, far-reaching sense, Earth's core is not just a layer in a geology diagram. It is one of the deep conditions that make a living planet possible, a hidden, beating requirement for everything that breathes beneath the stars. For all the stories we can tell about Earth's heart, there is a simple, humbling truth beneath them. We will almost certainly never go there. The core lies nearly 4,000 miles below our feet, so far down it may as well be another world. People have walked on the moon, sent machines beyond the edge of the solar system, mapped Mars in exquisite detail. Yet the center of our own planet remains forever out of reach, wrapped in rock and pressure and heat that no tool can survive. The deepest scar we have ever carved into Earth is the Kola Super Deep borehole in Russia. In the 1970s, engineers began drilling toward a depth of 9 miles. After roughly 2 decades, they stopped at about 7.5. That is less than 1/3 of 1% of the way to the core. Even there, the rock began to behave oddly, flowing slowly and squeezing the borehole like soft plastic. Temperatures climbed to roughly 350 degrees Fahrenheit, far hotter than expected, warping metal and destroying instruments. If 7 miles can twist our strongest tools, the conditions thousands of miles below become almost unimaginable. At the outer core, pressures rise to millions of times the air pressing on us at sea level. Temperatures are thought to reach around 7,000 to perhaps 9,000 degrees Fahrenheit, rivaling the surface of the Sunday. Steel would soften, titanium would fail, even diamond would deform or break. Electronics would not simply overheat, they would cease to exist. And even if some miraculous material could endure those conditions, there would still be the sheer scale, pushing any machine through solid rock for thousands of miles is far beyond anything we can plausibly build. From time to time, bold ideas are floated: nuclear blasts to fracture the crust, self-melting probes that sink under their own heat, but the physics tends to close each door. Explosions would create new molten rock that seals itself. Melting probes would bleed their heat into the surroundings and stall long before reaching the deep mantle. Fantastical as they sound, most of these schemes end in the same quiet conclusion: the core is not a place we will touch. So we listen instead. Earthquakes send waves through the planet, and those waves behave like soft X-rays, carrying information from the layers they cross. By measuring how fast they travel, where they bend, where they vanish, seismologists draw ghostly maps of the interior: the thin crust, the thick mantle, the liquid outer core, the solid inner core, and the subtle transitions in between. In laboratories, diamond anvils and powerful lasers compress tiny samples of metal to millions of atmospheres for a heartbeat of time, revealing how iron and its alloys behave under conditions like those of the core. High above, satellites watch the magnetic field. As its strength shifts and its poles wander, those changes reflect slow rearrangements in the molten metal beneath us. The sky and the ground together become windows into a realm we cannot reach directly. Our tools are still young. Seismic networks grow denser, computer models grow more detailed, experimental techniques grow more precise. Some dream that one day tiny autonomous probes, perhaps built with advanced nanotechnology, might hitch rides on natural currents inside the mantle, drifting slowly downward and whispering back data as they go. For now, those are only gentle speculations, but they say something about how deep our curiosity runs. Even with all we have learned, the core keeps its biggest answers close. We know it is mostly iron and nickel, but the numbers do not quite add up for pure metal. There must be lighter elements mixed in, perhaps carbon, sulfur, oxygen, silicon, maybe even a little hydrogen. But we do not yet know which combination or in what proportions. Each possibility paints a different picture of early Earth. More carbon would hint at building blocks rich in volatiles. More sulfur would tie our planet's birth more closely to certain types of meteorites. The same chemistry that shaped our core could be shaping the hearts of planets around other stars. But without a sample in our hands, we can only let physics and waves narrow the possibilities. The exact temperature of the core is still uncertain too. Estimates differ by hundreds of degrees. That may sound small, but in the deep interior, it changes how quickly Earth cools, how fast the inner core grows, and how long the geodynamo can keep turning. A hotter core points to a younger inner core and a magnetic field that may endure for many billions of years more. A cooler core would suggest an older inner core and a field that might begin to fade sooner. Even the age of the inner core itself is unresolved. Did it begin to crystallize almost 4 billion years ago when Earth was still very young, or only around 1 billion years ago when life had already covered the seas? Each scenario rewrites our timeline. In one, solidification has been feeding the dynamo for most of Earth's history. In the other, the dynamo must have relied on different energy sources for a very long time before the solid seed appeared. Seismic waves hint at uneven growth, differing crystal alignments, and perhaps a small inner core. One hemisphere of the inner core seems to be growing faster than the other. The innermost region seems to have a different orientation than the shell around it. These patterns suggest multiple stages of cooling, phases of iron we do not fully understand, maybe even exotic states of matter that only appear under the most crushing pressures. The future of the magnetic field is another soft unknown. We know the field has flipped many times, sometimes weakening dramatically in the process. We see places like the South Atlantic anomaly today, where the shield is noticeably thinner and satellites feel the increased radiation. Yet we do not know if we are watching the first murmurs of a long reversal or simply another temporary wobble. Will the field remain strong for another billion years, or is it already starting a slow decline? The answer is written in the way the core evolves, and that evolution is still only partly sketched. Even our best technique, seismic probing, has its own horizon. Quakes do not happen everywhere, and not all are large enough or aligned well enough to illuminate every corner of the deep interior. Our maps of the core are detailed in some places, blurred in others, with patches of uncertainty where the wave paths are sparse. It is like trying to understand a house by listening to echoes through the walls. You can make out rooms and staircases, but some corners will always be dim. Beyond the physics, there are questions that stretch toward life itself. Did the timing of inner core growth help stabilize Earth's climate just when complex organisms needed it most? Do reversals and field fluctuations gently influence evolution by changing the radiation environment? Or are their effects too subtle to matter? Could shifts in the core have played some part, however small, in past extinctions by briefly weakening our shield? These ideas sit at the edge of what we can test, bridging geology, biology, and astronomy in ways that are still more wonder than certainty. And then there are the possibilities we can barely frame. Superionic states where ions wander through a rigid lattice, unfamiliar alloys with strange conductivities, phases of iron that blur the line between solid and liquid. They may or may not exist in the heart of our world, but the fact that they are possible reminds us how incomplete our picture still is. No one will ever stand at the center of Earth. No camera will pan across the boundary between the inner core and the outer core. Our understanding will always rest on echoes, on flickers in the magnetic field, on rare gases rising in volcanic plumes, on tiny samples crushed between diamonds. There will always be gaps, disagreements, new interpretations. The core will remain partly hidden, even as we learn more about it. And yet, for something we will never touch, It shapes almost everything that matters. It holds our magnetic shield in place. It helps keep our air and oceans. It quietly guides the conditions that let life breathe and think and wonder at all. Somewhere far below, iron turns and flows in the dark. Above it, continents drift, oceans sigh against their shores, and the night sky stretches over us like a patient ceiling. Between the two, a long chain of cause and effect ties our quiet rooms to that unreachable heart. Every tremor, every shimmer of aurora, every shift in a compass needle is a small reminder that the planet is alive inside, and as long as it is, we will keep listening.